Okay, so today we are interested in classical information theory. And so this started essentially in the 1940s, and it was really the work of Claude Shannon, who initiated this field of research, which is quite important today. So many people typically more in math or computer science departments that are interested in studying really information theory, and information theoretic concepts are used in a very broad range of fields. And so Shannon essentially asked himself two fundamental questions. So two fundamental questions that he could answer, actually. So the first question is, by which amount or by how much can a message be compressed? And so to answer this, Shannon derived the so-called noiseless coding theorem. And in the second question he answers is, at what rate can one reliably communicate or transmit information over a noisy channel? And so this gives rise to the second theorem of Shannon, which is the so-called noisy channel coding theorem. And these are the two theorems that we are going to discuss today. And so on the way, this will allow us to introduce some interesting notions like Shannon Entropy, mutual information, and so on. So let's start with the first question. And that has to do, so that will lead to the concept of Shannon Entropy. So this is the question, by how much you can compress a message in general. So let me start with a sort of little example here. So let me write this. So I guess all of you, even those who are not fluent in French, can understand what it means, right? So am I right? Or can someone not understand what it means? Okay, good. So you all understand what it means. Now, obviously, you see what I did here is I got rid of the vowels, right? And yet, so of course I use much less information or much less symbols, essentially, but I can mediate the same information as if I would have added the vowels, as we usually spell out this sentence. So essentially, this already tells you that vowels they contain no information, right? You can just get rid of them and the meaning is still there. So vowels are just there aesthetically, right, to make the sentences sound a bit nicer. Now, if you take this reasoning further, right, you may ask, all right, what is the absolute level of compression of such a message, right? Because here I got rid of some symbols, but probably I can get rid of few more and it will still be understandable, right? So that's the idea of this first theorem of Shannon, where we are going to formulate this problem, right? So to make that formal, we are going to use the notion of an alphabet. So an alphabet is a set of k letters, which I'm going to call A1 to AK. And each letter has certain probability, which I'm going to write P1 to PK. And of course, these probabilities are sum to 1. And so what we are mostly going to use is a binary alphabet, as we typically use in communications. So that would be K equal 2. And so therefore, we just have 2 letters, which are 0 and 1. And these have probabilities, I'm going to call them P and 1 minus P, right? Okay, so you see, we do already a sort of huge simplification here because, of course, obviously, I mean, our real goal will be to encode sentences, right, that are encoded in some language. Here, however, what we are doing is that we are assuming that we have a binary alphabet. And so if you want in each individual symbol in a message, each letter has the same probability. So either P for a 0 or 1 minus P for a 1. So why is that a simplification? Because you see in French or in any other language, in fact, given previous symbols, the next one is in general not uniformly distributed, right? So if your previous symbol was a Z, for instance, it's extremely unlikely that the next one is also a Z, right? So therefore, there is some structure in the sequences of symbols, but this we're not going to take into account here, right? This would be too complicated. So here we just assume that every letter has the same, is given by this probability distribution independently of what comes before and what comes after. All right. So here is our main question. So can we represent messages with n letters using less than n bits? Okay, so obviously if I have a message with n letters, I mean here letters are bits, right? So I can do that with n, but I'm interested in compressing this information. So the point is we are going to look at typical messages with n going to infinity, right? We are only interested in the case of asymptotically long messages. So a typical message, well, it contains n times, sorry, here I did it the other way around. Okay, never mind. It contains n times p, np times the letter 0, and, okay, sorry, I write it the other way around. 1 minus p times n times the letter 1. Okay. Okay, so these are for typical messages, right? And so the question that we need to answer is how many such messages are there? Right, because clearly you see these messages, these typical messages, they are the much more likely messages, right? Of course, there is also a message that has only the letter 0 n times, but that, you know, has a significantly lower chance of happening, and in the asymptotic limit, it has a probability that is completely negligible to happen. So as long as I can encode those messages that are relevant, so the typical ones, I'm good, right? I'm able to compress all the relevant information. So the answer is that there are n choose np. Okay, this is the number of typical messages. And so essentially we are going to develop this expression and find how many bits we need to describe this number of typical messages. And the point is that this can, in general, it can be much, much smaller than 2 to the n, right? Because so 2 to the n is the total number of messages, right? That we can encode with n bits. But the point is this number of typical messages will in general be much smaller, right? And so essentially to calculate that, we are going to look at the log of this quantity. So that is the number of bits needed to describe these messages. And the point is that this is given by n times the some function h of p, and this thing here, this is the Shannon entropy. Okay, so the Shannon entropy h of p is defined like this. It's minus p log p minus 1 minus p log 1 minus p. Okay, and okay, there is a convention, namely that 0 log 0 is equal to 0. Okay. So this is our binary Shannon entropy. It takes this form, right? And okay, so here I didn't do the derivation. I think it's exercise number 1 this week, so I encourage you to do it. It's not very difficult, but it's quite enlightening to see how it goes. And to do this, you need to use this Stirling's approximation. Okay, so I let you discuss it and do it in the exercises. So now let's discuss a few properties of this Shannon entropy here. So if you have, so let's first start with a very simple and boring case. Imagine that you have, so this is, let's say, case 0. You have a deterministic alphabet. Deterministic alphabet, which means, for instance, that p equals 0, right? So that means there is only one message. It's the message that contains the symbol 1, all that in every place, right? Now that, you see, because of our convention, then the entropy here is 0. Okay, so that means that in order to encode any message here, well, we need 0 bits, right? So let me remind you, this is this thing here, this is the number of bits to encode the typical sequences, the typical messages, right? So 0 looks like it's very small, but of course this is correct, because in this deterministic alphabet there is only one letter, so there is only one message. And if there is only one message, I don't even need to communicate it, right? Because I always know in advance what this message is going to be. So a more interesting example would be case 1. That would be for a fully random variable. So that would be when p is 1/2, and then the entropy here is maximal, it is 1, okay? By the way, if I have a deterministic alphabet with that has only the letter 0, it has also entropy 0. So now I can make a little plot of my entropy function. So P goes from 0 to 1, and it will have a maximum at 1/2. So at 1/2, the maximum is 1 bit. And then the entropy function is a sort of bell-shaped like this. Okay, and it is, obviously it is symmetrical around this axis here, right? Because if I use letter 0 with probability P or letter 1 with probability P, it's just the same, right? I've just changed my convention of notation. All right, any questions so far?
I do have a question.
Good.
What do you mean exactly by typical message? Is it the relevant messages?
Well, you see, so in my, yes, the other relevant messages, right? So the point is, so I have an alphabet where letter 0 has probability P and letter 1 has probability 1 minus P. And therefore, if I have a sequence of letters, a message, I can attribute a probability to it, right, of happening. Now, what I'm saying is that when you have long messages, it's only those typical messages that have non-vanishing probabilities, right?
Okay, okay.
All the others, they have probability 0, essentially, right? Negligible.
Yeah, okay.
Okay, so that's why you can just focus on typical messages.
Okay.
Yes. So I mean, you see, you can think of it like this. So far, you could say I'm trying to derive a sort of lower bound on the number on the compression rate. Okay, because the point is, so if I was not able to take all typical messages into account, then I would get into problems, right? My compression wouldn't be a sort of lossless. Okay, because if I forget some typical messages, I mean, why these messages and not others? So therefore, it must be that my code is not good, right? So I should at least keep all messages. Sorry, all typical messages, right? Later on, in fact, we will see. Okay, at least with an example, that this is necessary and sufficient. So this lower bound I can actually reach by a specific code in general. Okay, so there exists a way of encoding my information which achieves the bound here given by the Shannon entropy. That's not obvious, but okay, good. So here we did the binary case. One can also do the general case when you have an alphabet with more letters. Okay, maybe you can just take a look at the notes. It's really exactly the same. Okay, you see this equation here. So the only interesting thing is how the entropy generalizes. So instead of having the binary Shannon entropy as here, you would have the denary entropy. And so you see here, you see the construction of this equation, right? So for each symbol, I have its probability times the log with a minus sign in front. And if I have more symbols, okay, then I just keep adding terms here with the corresponding probabilities. All right. Okay, so let's do an example. That's actually interesting. So this is an example about Shannon compression. So it's an example where we have an alphabet, and we will show what is a code to compress that alphabet at the Shannon limit. So here is my alphabet. I have actually here 4 letters. Let me write them 1, 2, 3, 4. And so maybe I also write here the probabilities of each of these letters. For letter 1, it's 1/2, 1/4, 1/8, 1/8. Okay. Good. Okay. So now I will define my code. So that means how do I encode now each letter? So it goes like this. Okay, so you see it's a little bit astonishing because my code, okay, it's a binary code, but I'm using sequences of bits to encode these 4 things, and these sequences have varying lengths. Nevertheless, I can show you that this is the right thing to do. So let's compute here. Let's compute here the average length of a coded message. So that is 1/2 times 1 plus 1/4 times 2 plus 1/4 times 3. Okay, so I'm just taking the length of my code here, right, multiplied by the probability of having the corresponding letter. So if you calculate that thing, this is 7/4. Okay, and of course that's an improvement, right? That is smaller than 2, because so 2 is what I would have for the non-encoded, for the initial alphabet, right? I have 4 symbols, so each symbol is encoded in 2 bits. So originally I would have 2 bits per symbol. And so when I use this code, I reduce it to 7/4. And in fact, one can check that the entropy here of this, so the entropy of this alphabet here with these probabilities, this is actually 7/4. Okay, so here we do reach. So we do reach the Shannon limit. Okay. So maybe we can actually just formalize the theorem. So you see here I'm using this notation with, so capital X denotes the variable that has as realization these letters here. So let me use that as a general notation, right? So Hx is the optimal compression rate. Okay, so this is for the variable x. And so the variable x, what it means is that it has letters x and probabilities px. Okay, and so this is really the optimal compression rate that you can achieve, right? And the point is, if you would, so when compressing at a, okay, in the notes I wrote a lower rate, so we just define what it is. So if you try to compress at a rate R that is smaller than the Shannon entropy, then one introduces necessarily errors. Okay, and that happens with a non-negligible probability. So optimal compression is given by the Shannon entropy. You can actually, this is reachable, and this is the optimal, right? If you would try to compress more, you start to lose information.
But what about, sorry, I have a question.
Yes?
What about if you have different codes and you would have, for example, for this same probabilities, 0, 1, 1, 0, 0, 1, for example. So you would have...
If I go back, you want to go back to the example?
Yeah, the example. So you have two codes of one number and 1 bit and two letters with 2 bits. So that would change the average length. It would be smaller than 7/4, and then...
So if I would add a bit here?
Oh, for example, you have for 1, 0. For 2?
If I would put just the 1.
Yeah.
No, that's not possible, because you see, if I do it this way, by counting the number of ones, I immediately know what is the exact separation between the symbols. So what are the letters, right? You see, what is not trivial with this thing,
okay,
is because if I give you a string of bits, right, you will have to decode. So you will have to tell which letters have been encoded.
So where's the space?
Where is the space, exactly? And so if you don't respect this sort of structure here, you don't get it right. You will do mistakes.
Okay.
So that's why you need to have this increasing length here. So this is the idea. It's quite logical, no? I mean,
yes.
There is one symbol that is much more likely than the others. So this one you encode just with 1 bit, okay? And then there are the others. In particular, there are these two that are not very rare, but they are much less frequent. And so for these ones, okay, you need 3 bits, but overall you win a lot, because here you could somehow spare 1 bit in the code. Okay, does it make sense?
Yes.
It's a good question. Okay, so yeah, maybe one thing I can quickly tell you about is, people have been trying to, so I mean, beyond this beautiful mathematics, right? You could ask, what is the optimal compression for a message in English or in French, right? However, of course, this is a very difficult question, right? Just because you consider the fact that, given a letter, the preceding and the following letters are not uniformly distributed anymore, right? Because words have specific structures. But nevertheless, so some people have, tried to work hard on this problem. And so the best estimate that has been found is that the entropy of English is 1.5 bits per character. Okay, so let me mention this as a remark. In the English language, the optimal, no, sorry, not the optimal, but what is believed to be a possible compression rate is 1.5 bits per character. So this is quite amazing, right? Because it means that, language as we write it, as we use it, is extremely redundant, right? So the point is, you could probably encode the same information by using, just a bit more than 1 bit instead of 1 out of 26 letters, right? All right. Of course, if you would go to Chinese, for instance, it would be very different, of course, because their characters are words, right? So the structure of the language has a strong influence on these ideas. So now so before going on to the second theorem, let's think a bit differently in terms of the entropy. So more generally, the Shannon entropy H of X, this represents our ignorance about the variable X. Okay, so what this means is that if you have a box and this box samples from the variable X, so in each round it will give you, possible realization. So this is a typical notation for these things. So when you write symbols with a capital letter, this represents the variable, and so the small typeset, they are the specific realizations of the variable. Okay, so here I'm sampling from a variable, and so I have in a specific round, I have that this variable takes the realization small x. Okay, so I'm here, right? I'm the observer, and so I can think of what is the surprise of the amount of information that this observer gets by looking at the specific realization of that variable, right? In other words, what is the initial ignorance of this observer about this symbol that is going to come out, right? And that's exactly the entropy. Okay, so for instance, you see, if this is a deterministic variable, right, it always takes the same value, I have no ignorance about it, right? I know exactly what's going to come out. So the entropy is 0. If this thing is a perfect coin, right, with heads or tails with probability 1/2, my ignorance about each realization is maximal, right? So in every instance, I learn 1 bit of information when I look at a specific realization of the variable. Okay, so it's useful to think of entropy in this way, right? It represents the information that is mediated to an observer about something, and that, of course, is directly related to the ignorance that this observer has about specific realization of that variable. Okay, so that is going to lead us now to another notion that is important, that is mutual information. And so before we get there, we need to introduce a couple of other notions of entropies. And the first one is, so we start with conditional entropy. So that would be the situation where I have here another variable y, okay? And so imagine that the observer has access to y, okay? Now, the question we ask is, what is the ignorance that the observer has about x, given that he knows y, right? Now, if x and y are independent, well, that's the knowledge of y will not help the observer, right? So he or she will have the same ignorance. However, you see, if on the contrary, if x is equal to y, if they are perfectly correlated, well, then the conditional knowledge of y tells immediately the observer what is x, right? So then the conditional entropy will be 0. Okay, so this is the kind of questions we are trying to formalize here. So let's define this quantity. So this is, so we write it like this, right? So it's the conditional entropy of x condition on y. And so this is defined as follows. So this is the sum over y. So again, y are the possible realization of the variable y. We look at the probability of having y, and then we have the entropy of x conditioned on y being equal to specific realization, right? So that is quite a natural formula. Now, that thing here, we can, in fact, define via our notion of entropy. So that will be minus the sum over y, p of y. And now what I want to have here, this is the sum over x. And now I need p of x given y and the log of p of x given y. Maybe I put brackets here. So you see, this quantity I just evaluate as being just the entropy formula, but where each probability is now just conditioned on a specific realization of the other variable, right? So that sort of makes sense, because that thing here is again a probability distribution, and this I can assign an entropy to it, and it is this thing. And so now I can just develop this. So what I'm going to do is I put both sums here in front, and you see then I have p of y times p of x given y. So using Bayes' rule, this is simply p of x and y. And now I have the log of p of x conditioned on y. Okay, so that is my formula for the conditional entropy. And so loosely speaking, this represents the number of additional bits. So that would be, if I'm still in with a binary alphabets, necessary for describing x, given I already know y. Okay. So you see the idea of what we are doing, right? So the point is that there are observers, and knowledge can be obtained from different sources, right? And each one is represented by a variable. And so therefore, I'm interested to see how knowledge is combined, right? So once I start to learn something, how do I evaluate my ignorance about the rest, and so on. So now we can define another notion. So this is the joint entropy. So this is probably more natural to see. This is, so I'm interested in the entropy of a pair of variables. So that is really just applying the usual formula. So now I have to look at the probability of a realization of every possible pair, right? And then I just evaluate this thing here. Okay, so that's the joint entropy. Now, why did I introduce this? Is because, of course, there is an interesting connection now between the joint entropy and the conditional entropy. So if I use Bayes' rule, right, I can check that the joint entropy is what? Well, it's the entropy of x plus the entropy of y, given that I know x. Okay, and this is very nice and very intuitive, right? Because what is my ignorance about this pair of variables, x and y? Well, the point is I can somehow decompose this, right? It's a sort of chain rule, if you want. So my ignorance about a pair of variables, well, is what? Is my ignorance about the first, so it's h of x, plus my ignorance about the second one, h of y, but given the fact that I already learned x, right? So this, the second term here is not h of y, but it's h of y conditioned on x, right? So of course this goes also the other way around. This is equal to h of y plus h of x given y. Okay, so this is the chain rule for entropy. And of course, I mean, it goes on, right? If you have the entropy of 3 or 4 variables, you use the same idea. Okay, so now we also get an interesting formula, namely that you see the entropy, the joint entropy, it's always upper bounded by the sum of the entropies, okay? And this is because h of y given x, this is always smaller than h of y, okay? So the reason for this, so the point is, if I have additional information, so having additional information never increases my ignorance. Okay, so my ignorance about a variable y, imagine I would have additional information and know x, so my ignorance about y cannot increase, right? But it could decrease. So that's why here I have an inequality. Okay, and so this inequality here is interesting because this showed that entropy is sub-additive. Okay. So now a couple of remarks about this. So in fact here we get equality if and only if x and y are completely independent. Okay, and this makes sense, right? If there is no correlation about between two variables, then your ignorance about, so when you calculate the total, the ignorance about the pair, the total, well, you have the entropy of the first, and then you have the entropy of the second. That should be the entropy of the second condition on the first, but because this conditional entropy is equal to the non-conditioned entropy due to the independence of the variables, then I would have equality here, right? But in any other case, so if there is the slightest correlation between the two variables, then the joint entropy is smaller than the sum of the entropies. All right. Maybe in fact we could also do the opposite case. So let's do on the contrary. If x is equal to y, right? So if the two are perfectly correlated, okay, then of course the entropy of the pair is just equal to the entropy of x. Okay, because the second term, the entropy of y given x, this is 0. Okay, since h of y given x is equal to 0. Okay, so now let me introduce now mutual information. which is precisely being, this will be a quantifier of the common information between two variables, right? And so how should this thing be defined? So I denote it like this now. So this is my mutual information between the two variables. So that thing is the following. So this is my entropy about X minus the, you see, so this thing here can be seen as the reduction of the entropy on X given that I know Y, okay? You see, because I take the entropy of X if I don't know Y, and if I subtract to that the entropy of X when I know Y, this difference is going to be a good measure of how X and Y are correlated. And of course, I can also do this the other way around. This is H of Y minus H of Y given X. Okay, so these are two, these are the definitions of the mutual information. But now I can use my chain rule in order to get a nice and symmetric formula for this, which is that the mutual information is H of X plus H of Y minus H of X, Y. Okay, so I just, you see, I for instance, from this equality here, I get an expression for the conditional entropy, and then I plug it in here, and I get this. And if I do it the other way around, I also get the same thing. All right. So maybe let me continue for a couple of minutes on this, and then we can do a small break. So take the case where X is equal to Y, okay? Then I see that the mutual information between X and Y, this is the entropy of X, okay? So for instance, if X is a randomly uniform bit, right? Then I have, and if X is equal to Y, then I have a sort of, there is a common piece of information between X and Y, okay, which is, in fact here, which will be one bit, right? Namely the entropy of the symbol X. So if on the contrary, X is fully independent of Y, okay, then my mutual information, well, you see, if I look at this expression here, right, if the two variables are independent, well, then this conditional entropy here is just equal to H of X, and so the mutual information is 0. And so in general, there is a neat way to get some intuition about this. It's by using Venn diagrams. And so here is how it goes. So Venn diagrams are these potato ensembles. So I have here, so I have two blobs, right? So the left one will represent the variable X, and essentially I will associate to its area, let's say, the entropy of X. And then I would have, for the second blob, that would be associated to Y, so I have the entropy of Y. And now you see clearly the mutual information between X and Y, this should be this central piece, right? This is what X and Y have in common. So mutual information I will put here. And what is left here on the left side, this is the conditional entropy. This is my ignorance about X if I know Y, right? So this is everything that there is in X that is not in Y. Okay, it's this area here. And similarly, this is H of Y given X. And now you see from this potato, from these Venn diagrams, this is find a very nice way to remember all these relations here, because you see, so the mutual information is what? Well, it's the entropy of X, so it's this area, plus the entropy of Y, it's that area, except that now, so it's the sum of these two, okay, minus the total area, okay? So when I take the total area, I have this, and so you see the difference between the two is that in the first case, I have counted twice this middle region here, right? Once in X, once in Y. And so when I calculate this thing here, okay, I see immediately that I just get the intersection here, which is the mutual information. All right, does that make sense? Okay, good. So if there are no questions, I guess it makes sense. So I think it's a good moment to make a little break. And so we can reconvene in a couple of minutes. And if there are some questions, I'm of course happy to answer. So are there some immediate questions, or can I just go and stop the recording for a minute? Okay, good. Then I go and stop. I was wondering if it would be the same nightmare again, but it works well now. Okay, good. So now we have all the tools that we need to formulate the second theorem of Shannon. So this is the noisy, maybe I should write noisy channel coding theorem. And so here we are looking at the following situation. So we have a sender and we have a receiver. And these two, they are connected by some channel which is noisy. Okay. So first of all, why is that different from the first theorem? I guess it's pretty obvious, but the point is that the noise of the channel may, sort of introduce errors and sort of, if you want, a mixing between the different messages, right? So one typical message could be taken for another one, and so therefore the receiver and the sender cannot communicate reliably, right? So here we want a situation where, again, we're interested by determining how much the information can be compressed, but we have this additional constraint that the sender must be able to send basically any information to the receiver, and the receiver can decode it reliably. Okay, so what we need here is we need to introduce our variables. So for the sender, we have the following. So we have some, we're going to say that the sender samples from a variable capital X that has realization small x with probabilities px. And so for the receiver, we in general have going to need a different alphabet, different variable. So it's, of course, it's a different variable because the probabilities may change, but in general may also be a different alphabet, right? For instance, you know, it could be that the receiver receives nothing. Right? There must be a symbol for nothing, and that symbol is not present in the alphabet of the sender, right? But you could imagine other things, right? Where for instance, this noisy channel here is transforming some binary alphabet into some quaternary symbols or whatever. All right, now once we have this, we also need a model for a channel. And so our channel will generally be described by a conditional distribution of what arrives at the receiver here, so y, condition on what has been sent, namely x, okay? So for every pair of symbols y and x, you determine this conditional probability, and then that conditional probability distribution describes your noisy channel. Good. Now, the point will be, so the theorem will be that essentially, so let's write it like this, but this is just to get the intuition. So the theorem essentially is that the maximal rate of communication is given by the mutual information. Okay, so but we'll make that a bit more precise. And so in fact, we're essentially going to discuss one example of a noisy channel, and that is the so-called symmetric binary channel. It's probably also the most, it's the simplest, but probably one of the most realistic cases as well. And so that is, so this binary symmetric channel, this is defined by the following. So this is a case where everything is binary, right? So the sender and receiver alphabets are binary. And so I need to tell you what is the probability of receiving 0 given that 0 was sent. Okay, so this will be 1 minus p. And so that immediately means that the probability to receive 1 when 0 was sent is p. Okay, and similarly, this is in fact equal to the probability of receiving 1 if 1 has been sent. And therefore, this is the same as the probability of receiving 0 given 1 has been sent. Okay, and so these cases here are the errors, if you want, right? So this is when the channel here may apply the sort of bit flip, if you want, to your symbol. So an error occurs with probability p, and with probability 1 minus p, you have no error. Okay. Okay, so now what are we going to do? Our goal is to construct a family of codes. So here we are again looking at messages of you know, long sizes, and typically going infinity. And what we demand is that that at the end of the day, the probability of an error in the communication is vanishingly small, right? So that should tend towards 0. Okay, so this is so we are going to want to define a recipe, right, for communicating over this noisy channel. And so what is a code? Well, a code, it's a set of 2 to the k messages of n bits, and these are the code words. Okay. So essentially, we are going to encode information on blocks of n bits. Okay, and in principle, there are 2 to the n possible messages we can have, right, on these n bits. However, due to the errors, you see that you see, for instance, the message. You see, so the message, to take message 1, that would be 0, 0, 0, 0, 1, and message 2, that would be 0, 0, 0, 1, 1. So these are 2 messages that are, you see, somehow they are very close in the space of messages, right? Because you see, I just need 1 error on this symbol here to transform message 1 into message 2. Okay, and so the idea is that if I had instead another message, message 3, which would be 1, 1, 1, 1, 1, 0, that message is, you see, intuitively, it's much further apart from each of these 2 messages, because I need many errors, many bit flips here to transform this one onto either of these, right? So that's the general idea of code words, right? I will be willing to use a subset of possible messages, right? I'm only using 2 to the k messages out of the 2 to the n that are possible. And somehow I want these code words to be sort of far apart from each other, right? So I want that you really need quite few errors in order to transform one code word into the other. Okay, that's the idea. So now we can sort of define the rate of a code. And the rate of a code R, this is k to the n, okay? So you see, I have a sequence, so I'm using blocks of a given size n, and k is in a sense the number of these blocks I'm able to use. So the more, you see, the more blocks the more sequences I'm allowed to use, right? The larger the k, the better the rate, right? The ideal case would be that k is equal to n, then I have a rate of 1. But typically, when I have errors, the rate is going to be smaller than 1. But clearly, you see, what I want what I want is to find the largest possible k, such that, you know, I can sort of handle errors. Okay, I can keep them in control. Okay, so the intuition is that all code words should be sort of far apart from each other, in the space of 2 to the n possible messages. Okay, so we can make that a bit precise. So given 2 messages, we can define their Hamming distance. So given 2 messages, we can define their distance. This is the concept of a Hamming distance. and this is how many bits must be flipped to transform one message into the other. Okay, so you see, for instance, in my example before, these two messages here, they have Hamming distance 1, right? I only need to flip the fourth bit here to transform one into the other. So they are as close as it's possible in this space of messages. The Hamming distance between M3 and M1, it's 5, right? Because you see, I need to flip all bits in order to transform M1 into M3. The Hamming, so this is maximal Hamming distance here. And the Hamming distance between M2 and M3, it is 4, right? The fourth bit is correct, but all the others have to be flipped. Okay, so that gives an idea of the, of the distance between these messages. And of course, this distance tells us something about how robust to noise these messages are, right? Because a noise, an error, this is a bit flip. And so the number of bit flips I need to transform one message into another tells me how robust to noise these two messages are, essentially. Okay, so now you see we can get a very crude approximation on the rate of our code. So if I have messages of n bits of length n, so this is, well, in fact, this is 4 messages of length n, then typically n times p bits will be flipped. Okay, because my channel, which is, let me put you the equation again. So my channel is given by this here, right? And so an error occurs with probability p, and of course the errors are independently distributed, right, over each letter in my message. So for each letter, I have a probability p of an error. So if I have a message of length n, then typically I will have n times p errors. So n times p bits will be flipped. So therefore, so hence, every message, so if I start from a given message, this message, when I send it through my channel, it will scatter in a sphere of radius and p in the space of messages, right? So that means that all messages that are at a Hamming distance of np, right, they are, likely to be reached when I start with my initial message, right? So I need to figure out how many, right, of these messages are there in this sphere, right? Okay. So the question is, how many messages does such a sphere contain? Okay, now in fact we know already the answer, because the answer is n choose np, right? You have you have a message of size n, and you have, out of these n, you have to choose fraction np. Okay, sorry, a fraction p actually. So you have np letters that you will be flipped, and these can be any of the letters, of course. So this, we know already that this is 2 to the n times the binary entropy of p, right? Because it's exactly the same calculation as what we did for the noiseless coding theorem. Okay, so here is our situation. It's easy to understand graphically. So I have 2 to the n messages, right? So this is my space of messages. And now, so I'm going to start with different code words, okay? So let me say that this is code word 1, code word 2, etc., code word 2 to the k. Okay, so I have many code words. And so these code words are the specific messages I'm using in my communication, right? The others I'm not using. Now, the point is that because of the errors in the channel, so we know that each of these will scatter, right, through nearby messages, right? And the radius of this sphere corresponds to a Hamming distance of n times p, right? I have the same thing here, and I have the same thing here, okay? Now, you see a very crude approximation then for my code to work is that if I sum the total volume, right, of each of these spheres, that is, if I count how many messages there are in each of these spheres and I sum it, that should not exceed the total number of messages, right? So intuitively, this is the best thing I can do, right? I have all these elements and I have to combine them in spheres. And so I'm looking for the, the best filling somehow of this space, okay? Now, to find it is maybe difficult, but at least to get an upper bound on how many code words I can take, I can just say, okay, if I sum all the messages that are contained in all these spheres, this should not exceed the total number of messages that there are, right? So this is what we are going to use. And so therefore we see that now in each sphere, this is the number of messages, and I'm saying I have 2 to the k spheres, okay, because this is the number of code words. And so that thing, I can rewrite it, that is 2 to the n so I can rewrite it like this, right? Here I just use the definition of the rate. And now my crude approximation is that this should not be bigger than 2 to the n. Okay, and so you see from this I get a neat, simple, neat formula, which is that the rate should be upper bounded by 1 minus the binary entropy of p. Okay, and this optimal rate here, this I'm going to call C of P. This is the capacity of the channel. Okay. Now the point is that this capacity, this maximal capacity, this is reachable. So in fact, it is possible to attain the capacity. In fact, the capacity is how it's defined, right? So in general, the noisy channel coding theorem defines a quantity, namely the capacity of the channel, which is the maximal rate of my code. And for this particular case here of the symmetric binary channel, it turns out that the capacity is this quantity. So in fact, maybe I should not put 3 bars here, but I should just put 2. Okay, because it's not a definition, but the capacity turns out to be equal to this thing. So from this very crude approximation, I already got the correct bound. Okay, so maybe let's define now this noisy channel theorem. So, our noisy channel coding theorem. So this thing, it tells us that the maximal rate, so that is called the capacity of a channel. So this thing is given by, so I call it C, and that is the max over, let me call it Q of X, the mutual information of X and Y. Okay, so you see, so I'm trying to, so remember the setup. I'll put it here. Okay, so here is our setup. So we have a sender and a receiver, and you see, I would like to, somehow maximize the information between the sender's variable and the receiver's variable, right? So of course, it is natural that the mutual information between sender and receiver enters the game. Now, in general, the point is, I'll be willing to maximize this quantity, right? So the probability with which I use a certain letter X, this is up to me to choose, right? In principle, I can play with this probability distribution in order to maximize my mutual information here. And so that's what I'm doing here, right? I'm maximizing over the distribution of the sender's symbols, okay? Okay, so now for the symmetric binary channel, we can actually check that everything works nicely. Yes, sorry, maybe I should make complete the formulation of the theorem. So the theorem shows that there exists a family of codes achieving rate C, okay? And it also shows that any code such that the rate would exceed C necessarily introduces errors. Okay, and these are errors that have a non-negligible probability. Okay, so it's very similar to the first theorem of Shannon. It's just telling you that this is really the best thing that you can do. Okay. Okay, so that's our theorem, and now we're going to check. Okay, check for the symmetric binary channel. Okay, so what do we have here? Well, we have our sender, and our sender can choose between two letters, 0 and 1, and I'm going to call Q the probability to choose 0, and 1 minus Q the probability to choose 1. So this is this Q of X, this is my degree of freedom here. Then I have my symmetric binary channel, and then I have my receiver, okay? And my receiver also has 0, 1 as alphabet. Okay, so now I start from the theorem of Shannon, so I'm interested in the mutual information between X and Y. And so that thing is the entropy of Y minus the entropy of Y condition on X. Okay. Now, I'm interested in the second term. So what is the entropy of y condition on x? This is the sum over x. Okay, let me call it q of x. Oh, sorry, maybe it's not an. Okay, maybe I should write p of. Let me write p of x. Okay, so it's p of x times the conditional entropy of y given x is equal to x. Okay, so that's the formula I'm interested in. Now I should just point out that for each x, I have in fact that the entropy of y condition on x, this is simply the entropy of p, right? Because with probability 1 minus p, I see y equal x, and with probability p, I see y different from x, okay? So therefore, I see that my mutual information, this is h of y minus h of p. Sorry, it should be q, actually. This is what I call q. Okay, so yeah, you see q is the bias of my distribution. Sorry, hope it's clear. Okay, good. So now what I'm left with is that I'm, no, sorry. Yeah. This is h of p, yes. So sorry, p is the noise. Sorry for the confusion. So this is the noise of the channel, right? So this is h of p, this is correct. And now what I'm left with is an optimization over the q, right? And the q, of course, influences the entropy of y, right? Because if the input symbol x is biased towards one value, so will also be the output symbol, right? So when do I get the largest contribution here? Well, this is when the alphabet is uniform, right? So when the symbols 0 and 1 have the same probability. Okay, so this is maximized when q is equal to 1/2. Okay, so therefore I get that the capacity is equal to 1, okay, because then the entropy of y is equal to 1 minus h of p. Okay, sorry, you can't see anything. Let me put it back here. Okay, so sorry for the confusion here. I hope it's clear. Ask me if it's not, and I can maybe rewrite it. But okay, you see, here we have looked at this very simple, but it's quite a realistic type of channel, right? This symmetric binary channel. And it turns out that for this channel, you know, one can really, so it's simple to evaluate the capacity. For more general channels, this is really, really difficult, but for the binary symmetric channel, one can do it. And moreover, we can actually construct a family of codes that achieves this capacity, right? And this is the idea behind the construction I gave before. All right, so here we are at the end. So are there any questions on this? Okay, so can still ask in a minute after the end of the lecture. Maybe just to conclude, so you see, so these are the main, the basic elements of classical information theory, these two theorems of Shannon. Now, of course, you see, when you say quantum information theory, you know, you could understand this as being the generalization to quantum signals, right? To quantum, where alphabets are given by quantum states of these ideas here, right? So if I have a sequence of n qubits, can I compress that in, you know, a smaller number of qubits? So these are questions that people have asked and addressed actually as well. But okay, this is much more difficult, I would say. So in the first year I gave this lecture, I discussed these questions in the very last lecture, but then I realized that I essentially lost everyone in the class. So since then I decided to abandon this last lecture on, you know, real quantum information theory as, you know, respect to classical information theory. But now I just say that it exists. Okay, so, you know, you should be aware that one can do similar things. However, the exact procedure and so on, this is much more difficult. All right, so here is a good place to stop. And I see you next week for the next lecture.